Hello, my name is Christopher Ward. I'm doing the Chapter 20 Reassessment, where you're taking a coil and you're turning it that way, 90 degrees. So the coil is initially it's at a position to receive the most amount of flux, and then once it's turned, it gets zero flux. That just relatively places it right there. So it's 50 turns. The radius is 10 centimeters, or 10 times 10 to the negative 2 meters. The average EMF is 0.687 millivolts, or 0.687 times 10 to the negative 3 volts. The area is just going to be pi r squared, which just gives you pi times 10 to the negative 4 meters squared. And I'm just going to keep it at that value just to have a more precise answer. All right, so theta 1 is 0 degrees. That's the degree, or that's the angle between the field and the direction of the coil. Theta 2 is going to be 90 degrees. So basically, you're just taking the coil and going like that. And then we have two equations that we can use to find B. We have EMF equals delta phi over delta t. We know delta t, we know EMF. And we have phi equals NBA cosine theta. We know N, we know the A, and we know the angles. So we take those and we plug those into there. It gives us EMF equals NBA cosine theta 1 minus, what should be, NBA cosine theta 2, which is just 0. So over delta t. And then we're just going to solve for B. So you multiply both sides by delta t, divide both sides by NA cosine theta 1. And that just gives you B. And then we plug in our values. And just in the calculator, it gives us 3.499 Teslas. Now this value would only be, so this value would be different if the latitude was changed, but could be the same if the longitude was changed, due to the fact that the magnetic field strengthens as you get closer to a pole.